Okay, time for Thermal Physics 6. So, once again, penultimate lecture of our second unit, which is kind of cool. Hopefully, Thermo has been just as exciting for you as it has been for me. So, we'll go through our learning targets, try and get through this lecture a bit more quickly because it is slightly shorter. So, I can explain the first law of thermodynamics. So, for those that don't know the laws of thermodynamics, other than the zeroth one, which we talked about already, we'll make sure that we go through the first one in this lecture. I can define the types of thermodynamic processes. I can describe the phase transitions of water and their relationship to internal energy. So, water is a fluid that we don't necessarily like a lot of up until now we've talked a lot about gases, but we want to make sure that we also talk about water as a liquid in terms of thermodynamics. And then I can summarize the role of the first law of thermodynamics in various processes. So, in previous sections of this unit, we actually, once again, we define internal energy, heat, and work in thermodynamics. And now what we're going to do, we're going to combine them all into one formula expressing conservation of energy in any thermal process that we talk about. So, two ways that we have learned to increase the internal energy of a system. You can add heat to the system, or you can do work on the system. And so, mathematically, what this comes out to be, and I'm going to double check, this definitely is on the reference table, I would hope. This is like pretty important. Yes, it is. Okay. So, look at that. You got another equation on your reference table, but I'm pretty sure this is the last one. For thermo, at least. So, mathematically, the change in internal energy is going to be equal to Q plus U. Once again, Q being heat and work being, or W being work. Okay. So if we take a look at the four different types of thermodynamic processes and their effect on the internal energy, we can actually come up with some really quick ways of being able to cancel some terms. So each process takes place in a situation where a particular thermodynamic quantity is fixed. We have seen isothermal, in which is constant temperature, isobaric, which means constant pressure, which means change in pressure would be zero. I don't know why I put constant here, but and then isovolumetric, which means constant volume, so the change in volume is zero. And then adiabatic is a new one that just means that there's no heat added or removed. So that just means that Q is equal to zero, which is going to reduce your first law of thermodynamics down to being just equal to the work done on the system if it's adiabatic. So once again, isothermal process, temperature is constant, so any delta T is zero. So for an ideal gas, if internal energy depends on T, or we know that internal energy depends on T, that would mean that internal energy is constant. So if that's the case, we have this reduced down to this here for an isothermal process such that the heat added is equal to the negative work. So, if you were to think about that physically, that just means that all of the heat that's added to the system is converted to work by the system. And that's actually really important when you start thinking about expansion and contraction of gases. So, we're saying, okay, we took all of this heat that we had and it's now going to be converted into work by the system. And once again, kind of important to just have an understanding of. So in physics, isothermal processes are generally going to involve very slow expansions and contractions. Any kind of clue that gives away that it's isothermal at constant temperature, if there's an involvement of a hot and cold reservoir, and I'll make sure that we go over some questions that look like that, or something is happening very slowly. This line here, this A to B, that is called an isotherm, so that's just an isothermal process, kind of like a shorthand of it. Okay, so some real life examples of isothermal processes include phase changes. So when we talk about phase changes, we're talking about a lot of times talk about water because that's the one that we definitely see the most. So in our very first lecture in AP2, I believe we we learned that the term phase refers to a specific state of matter, one of those states of matter that we were talking about being a solid, liquid, or a gas. So when a substance undergoes a change from one of those to another, it's called a phase transition. So phase transitions at a given pressure take place at a constant temperature are accompanied by the addition or removal of heat and may also involve a change in volume and density. So if we think about water freezing, water vaporizing, ice melting, or steam condensing, those are a couple of phase transitions of water specifically. So if you think about ice cubes, for example, they float in water, therefore ice must be less dense than water, and as a result, that's a really good way of looking at a change in density as you're undergoing a phase transition, for example. So if we take a look at this, you can see water transforms from ice to liquid water to steam as you add heat. So we look at this and this. Okay, so heat increases, temperature increases. We end up with our different phase transitions. So during the phase transitions, the graph is horizontal, so T is held constant while heat is added to the system. And this is a really important distinction between heat and temperature for that reason exactly. So we're holding T constant while heat is being added to the system or taken away from the system, depending on which way we're going. So while in a single phase, whether it be ice or water or steam, the temperature rises as heat is added. And you can see that as the linear relationships in here, which should make sense because if internal energy is dependent on temperature and temperature is directly proportional to Q plus delta U, then that should mean that if I increase Q, the temperature would increase and vice versa. So when a phase transition is taking place, the temperature remains constant. So where is that energy going to or coming from? Because you may have that question, and I know that we really want to learn about chemistry. So the energy is going into making or breaking bonds between the atoms or the molecules of the material. So if you think about water, when ice melts, the bonds that hold the water molecules in place are broken when you add energy to it. When that energy is removed from water at 0 degrees Celsius, the molecules bond again and crystallize into ice. And so you can kind of see how this keeps going back and forth with the bonding and unbonding or breaking of bonds between any atoms of a fluid that we're kind of talking about here. So isobaric processes, to move on from isothermal. Isobaric processes, we know that pressure is constant. So as if work is equal to negative P delta V, the work is done just as soon as volume changes. So if once again pressure staying the same, so any work that happens is going to be a result of an increase in volume. So because T is allowed to change, that means that the change in internal energy is also not zero. And so that means that since delta U equals Q plus W, heat that's added to the system causes the system to do work, and the internal energy of the system and therefore temperature are also going to increase. So isobaric is a little bit more complicated in that nothing really cancels out to zero, and that in order to find the work, you're going to have to find the area of this here. So that's just something to note, that we can't really reduce anything here as far as, like, yes, this is fixed, and yes, this is probably easy to figure out the work that's done here, but that's not always super simple, and we would still need to know what Q is above that as well. So just because the work is easy, it doesn't mean that everything to find is easy. So in an isovolumetric process, we know that volume is constant, so that means that P and T are both changing, and therefore the internal energy, obviously, hopefully. So if volume isn't changing, we know that there is no work done, and if there's no work done, the first law of thermodynamics just becomes delta U is equal to Q. So if you think about that in terms of a physical quantity of gas that you have, that means that the heat that's added to the system is what is going to cause an increase in the system's internal energy. So some clues that indicate that a process is volumetric, and I know I forgot to mention that with isobaric, but it really just is. It'll tell you if it's at a constant pressure. There's not really another way of kind of going around that. But so if something's isovolumetric, they'll say it's at a constant volume, or there's an involvement of a rigid container. A rigid container means that the volume is not going to change from that, or the piston is locked. If a piston is locked, then the gas can neither expand nor contract, and therefore the the volume is held constant. So adiabatic processes, no heat enters or leaves the system. So since Q is equal to 0, that means that the internal energy of the system is just going to be equal to work. Any work that's done on the system is going to increase the internal energy, and any work done by the system decreases its internal energy. One of the hardest parts here, one of the hardest parts here about an adiabatic process is that it almost looks like a 1 over x graph, but it's really not, and I'll kind of show you the next slide with this. And so on a PV diagram, you could definitely see a jump from one isotherm to another. It's not really a jump. It looks like 1 over x, but the graph is quite a bit steeper. So if you're really struggling with this, I encourage you to make sure you really know what 1 over x looks like if you were to put it in a calculator. So some examples of adiabatic processes include any kind of explosion or implosion or something that's highly insulated. So some clues that give away that it's adiabatic is that it is highly insulated, there's no heat transfer, which means Q is equal to 0, which is what I'm telling you here, or that it happens very quickly. If it happens very quickly, there is not enough time for heat to transfer, and therefore we deem the process to be adiabatic. Okay, so this is a nice little chart that kind of summarizes how whatever condition you have as a result of this process, and then how the first law is affected. The first law of thermodynamics is affected by that. So once again, the isobaric one is the one that's kind of tricky in that it definitely has the two terms, nothing is 0, whereas the other three, something is clearly equal to 0. But just remember that work, you can get that from the area under a PV graph, and then Q, most of the time you're going to get that with MC delta T as far as the problems that I've seen at least, but I will definitely double check that. So 100 joules of heat, and that's important too. Remember, heat is energy, so it's measured in joules. 150 joules of heat is added to the system, and 100 joules of work is done on the system. What is the change in the internal energy of the system? So we're talking about delta U is equal to Q plus W, and we have 150 joules of heat. And now we want to look at this. This is 100 joules of work that is done on the system, so that means that it is positive work. So plus 100 joules, so the total change in internal energy is 250 joules. So now we have 250 joules of heat is added to the system, and the system does 100 joules of work on the surroundings. So if the system is doing work on the surroundings, that means that this is going to be negative, okay? Because that means that the system is, if we're talking about work being done on the system being positive, this is the opposite of that. The work done on the system in this case is negative because the system is doing work on the surroundings. And again, I know this is probably a nightmare to keep track of when you're first learning it. I know I struggled with it at least. You guys are all brainiacs, so maybe you're not struggling with it, but I know that some of you are looking at this and just probably sighing, wondering what you've signed up for. Anyway, so 250 joules plus negative 100 joules. So your internal energy change is going to be 150 joules. Question 3. So if I take a look at this, and this is a very common AP-like question. So a sample of an ideal gas is taken through a closed cycle. Which of the following is true about the change in internal energy and the work that is done on the gas between point 2 and point 3? So if I look at point 2 and point 3, I can absolutely determine that this is an isotherm because it looks like a 1 over x graph as opposed to this, which is a very steep 1 over x graph, and that would be an adiabatic process. So if it's isothermal, that means that the change in internal energy is going to be equal to 0. So I can cross out D and E, and then I need to figure out the work. And obviously that's a little bit harder because the work here is clearly changing. Um, so what we can say here, or I shouldn't say that it's changing, but there clearly is work done. It's not 0. So what is kind of cool here, so we're talking about the work that is done on the gas, and that's once again really important here. So the area underneath this curve is positive, but if we're talking about the work that is done on the gas, the work is going to be negative, so you should get that. So another way of looking at this, the area under this, the work that the gas does is positive. So that means that the work that is done on the gas is negative. Hopefully that makes sense. I know there are so many rules to remember this, or for this unit, and I know that it's probably really challenging, and I'm sorry. Next one, because we're going to move on because it's challenging. So a sample of an ideal gas is taken through a closed cycle. Which of the following is true about the change in the internal energy and the work done on the gas between point 1 and point 2? So now we're looking at here instead. So from 1 to 2, that's a vertical line, so that's clearly isovolumetric. So that means that the work that is done is going to be equal to 0, and that's actually really great because it eliminates all of my other answers because none of those. But if you really want to think about it, you could sit here and calculate out the change in internal energy, because if there's no work done on the gas, that means that the change in internal energy is going to be equal to Q. And if we're heating the gas up, which we know to be true because if volume is not increasing but pressure is, that must mean that temperature is always also increasing. So this is going up. So your internal energy is going to be increasing because of an increase in temperature, and your heat is obviously going to be there as well because that is what, when it's isovolumetric, the internal energy is equal to the heat. Once again, I really hope this makes sense. I know that it is so many rules to remember, and I'll make sure that we practice as much as possible in class some more. Maybe we'll just throw out one of the labs if we really feel that we're struggling with this, and we could just go through a set of questions one day. As much as I know we want to play with fire, we'll kind of determine what you guys think is best for that. And we could go over like experimental design questions as well, so that you're not losing out on the lab experience itself. But I really do want to make sure that we understand these questions. So one more lecture of this, and then you guys look at that. We'll be one step closer to taking an exam on this.